I extended your submission date, so just upload it to Moodle, okay?
Okay. Now you have extended.
What?
You have do it.
Yes, yes.
Okay.
Yeah. You can submit now until I don't remember what date I put in, but just do it as soon as you can.
Okay.
Okay. Great. So today we will talk about the grand canonical ensemble. Okay, so this is an extension to the canonical ensemble. Okay, so when we talked about canonical ensemble, we said we have many systems, right, that can exchange energy between them, and we look at one system from these whole systems, and it means that we look at a system that can exchange energy with its surroundings. So this is the canonical ensemble. Now the grand canonical ensemble is just the same, except that it also can exchange particles with its surroundings. Okay, so the grand canonical ensemble exchange energy and particles. So in the system we look at, we don't have a constant number of particles and we don't have a constant energy. And the definitions and the equations in the grand canonical ensemble are very similar to the equations in the canonical ensemble. So we do the same thing. Yes, we write the partition function. Okay, so I write it here. I have small g and c for the grand canonical ensemble. So we write the partition function of the grand canonical ensemble, and again we're summing on all the possible states the system can be found. Okay, and we have here the same exponent of minus beta, and we have here the energy of the state. But now, because the system can also change particles, so we insert it as well into the partition function of the grand canonical ensemble. So we have the energy, and we add here minus the chemical potential times the number of particles found in state R. Okay, so we have a state R, it has some energy, it has a certain number of particles, and we're summing on all the possible states of the system. Okay, and then when we talked about the canonical ensemble, we talked about the free energy of Helmholtz, and now we do the same, but it is called the grand canonical potential. But it is just the same as the free energy of Helmholtz. So this is equals to, okay, it depends on T and V and mu, and it is equal to U minus Ts. This is the free energy of Helmholtz, and we add here the minus mu times the average number of particles. Okay, and if we want to write it with the grand canonical partition function, so it is just the same as in the canonical ensemble. We have minus kBt ln of the grand canonical partition function. Okay, and then when we have the partition function, we can get the grand canonical potential, and then we can get any thermodynamic term we want. Okay, so for example, the energy of the system equals to derivative of beta times this potential relative to beta, and the pressure equals to minus derivative of psi relative to the volume, and the number of particles equal to minus derivative of psi relative to mu, and the entropy equals to minus derivative of psi relative to T. Okay, same equations. Okay, and last time in the grand canonical potential, in the canonical ensemble, we talked on possibilities as well. So we can also do it here and say, okay, the probability to find the system in some state R equals to, and we have the same thing, so we have the exponent of state R, so we have minus beta, the energy of state R, minus this mu and number of particles, divided by the total partition function. Okay, so we can see that both ensembles are very similar. Okay, so now what we want to do is to see how we can connect between the two. Okay, how we can write the grand canonical partition function using the canonical ensemble. Okay, because it's really similar. So let's see how mathematically we can do it. Okay, so the grand canonical partition function is summation on this exponent, so we have minus beta ER minus mu and R. Okay, now we can say, okay, we have several states with some energy. Okay, so we can have, let's say, write it as summation on R on exponent of minus beta ER that dependent on the number of particles. Okay, the energy of the state depends on the number of particles, and we can divide it, the exponent to this energy and the number of particles. Let's just write it as n. Okay, so the energy of some state depends on the number of particles, and then we are summing on all possible number of particles in the system. So actually what we have here is for some number of particles, we're summing on all possible states. Okay, and then we can get the canonical partition function for some specific number of particles. Okay, so this is the canonical partition function for n particles. And then we're summing on all possible number of particles. So we get all possible states. But now we succeeded to write the grand canonical partition function using the canonical partition function. And sometimes it can be easier to calculate the canonical partition function it can be easier to calculate the canonical partition function than the grand canonical partition function. So we have that the grand canonical partition function equal to summation on all possible number of particles, and then the canonical partition function for specific number of particles n times the exponent of beta, mu, and n. Okay, so we need to do here one more step, because if we keep it this way, right, we will be we need to calculate the canonical partition function for every specific number of particles in the system, right? So we want to write it more generally, that it won't be dependent on n. Okay, this function has dependence on n, and we want to see what this dependence is and to find some general mathematical way to write this function. Okay, so we can sum on n easily. Okay, so now if we have a system of an ideal gas, okay, that means that between the particles we don't have interactions. So we can use the subsystem partition function for each particle, right? So in ideal gas, we can write that the canonical partition function for a specific number of particles n, that will be equal to the subsystem partition function for one particle in the power of n. Okay, and if our particles are identical, we're adding this division by n factorial. This is for identical particles. Identical particles. Okay, so if we have an ideal gas, the grand canonical partition function is now becoming 2, so we have the summation on n, and we have this, okay, let's write it, the subsystem partition function in the power of n times 1 divided by n factorial, and we have here the exponent e beta mu n. Okay, so this is a known Taylor series. Okay, we can write it as let's write it as e beta mu times the partition function in the power of n divided by n factorial. So this gives us exponent of this term inside the partnessness. I don't know. Okay, so we get here exponent of e in the power of beta mu times the subsystem partition function. Okay, and this solution we can use. Okay, so if we have an ideal gas, we can write the grand canonical partition function with the canonical partition function for one particle. Okay, so all we need to do for an ideal gas, we need to find the subsystem partition function in canonical ensemble for one particle, and then we have the function of the whole system. Okay? Great. So now let's see this in the most classic system with ideal gas, just So we have, let's do exercise, and we have find the grand canonical partition function for an ideal gas. And derive the entropy, pressure, and number of particles. Okay, so we have an ideal gas and we want to find the grand canonical ensemble, so we're just going to use this, this formula. Okay, we're just going to calculate this subsystem partition function for one particle and then get the grand canonical partition function for the whole system. Okay, so the partition function for one particle in ideal gas. Okay, so we want to sum on all possible states with their energies. Okay, but now when we're talking on ideal gas, okay, so this is a continuous system. Right? The energy of the particle depends on the particle momentum, right? And this is a continuous term. Okay, so the energy is continuous, so the summation needs to be continuous. So we're going to use an integral instead of this sum. So the partition function will be equal to integral, and because this is a continuous system, we have this h in the power of 3 factor. We have this factor to get the right units. And then we're summing on this exponent, so we have minus beta, and I'm writing the energy using this momentum. So we have p squared divided by 2m, and this p is a vector, and we're summing on all space, so we have dx, dy, dz, and we're summing on all momentum. Okay, so this solution you saw in the lecture, right? You did it in the lecture, great. So we can just write the final solution. So we have it's a bit long, but okay, we have 2 pi m kBt in the power of 3 divided by 2 times the volume divided by h in the third. Okay, for convenient, I'm going to denote lambda to be h divided by 2 pi m kBt squared. Okay, so I won't need to write this term every time, so just write lambda in the third instead. So the subsystem partition function for one particle equal to v divided by lambda in the power of 3. So the grand canonical partition function equal to, and I'm taking this term and putting it in the formula we found, and the grand canonical partition function is exponent of E beta mu times this partition function. So we have here V divided by lambda in the third. And this is the grand canonical partition function. Okay? Great. So we have the partition function. Now we want to find some thermodynamic sizes. We want the entropy, we want the pressure, and we want the number of particles in the system. Okay, so let's start with the entropy. Okay, so first, in order to find thermodynamic sizes, right, we first need to find the grand canonical potential. Okay, so we need to find this psi that equals to minus kBt ln of the grand canonical partition function. Okay, so let's take this size, insert it to this equation, and we get minus kBt exponent of beta mu times V divided by lambda in the third. And now we can derive the entropy, the pressure, and the number of particles from this potential. So entropy equals to, we have minus derivative of psi relative to the temperature so that will be equal, and we need to pay attention that this lambda, right, is also dependent on the temperature. Okay, so at total we will get that this equals to this exponent of beta mu times V divided by lambda in the third times 5 divided by 2 minus mu divided by kBt. Okay, this is our entropy. Now the pressure is minus derivative of psi relative to V. Okay, so we don't have any dependence on V in lambda, so we only derivative relative to this V. So we get minus kBt divided by lambda in the third, and we have the exponent of beta mu. Okay, so this is the pressure, and the last size, number of particles, so we do the same, and derivative psi relative to mu, and we get E beta mu times V divided by lambda in the third. Okay, so if we have this grand canonical potential, if we have this partition function, we can find any thermodynamic size of the system. Okay? Great. I can erase this.
Yeah.
Okay, so this was, let's say, more simple question. Now let's see more complicated question. Okay, so now we have given an ideal gas in a box with a some NS adsorption sites on its wall. Now each side can absorb at most one gas particle. Each one, so each absorbed particle gets minus epsilon energy. What else we need to know? So the gas particles are identical. And the total number of particles in the box is constant. And equals to some m, some parameter. And we have the number of particles in the gas, meaning excluding those particles in the adsorption sites. So this is equals to N1. Okay, so let's for a minute see with what system we need to handle here. So we have a box. Okay, and this box has adsorption sites on its walls. So we have adsorption sites on the walls of the box that each site can have 0 particles or 1 gas particle. Okay, so at most it can absorb 1 particle, so each site can have 0 particles or 1 particle. Okay, great. What else we know? So each particle in adsorption site gets minus epsilon energy, meaning energetically it is preferred for the particles to be in the adsorption sites. And the total number of particles in the box, meaning the gas particles and the adsorption sites particles, equals to n. So all the particles in the system is n, and the particles in the gas that are not absorbed is n1, only in the gas. Great, and now we want to start with A. Write the canonical partition function for the free gas particles. Okay, so when we are told to write the canonical partition function for the gas particles, we need to assume for the canonical partition function that the number of the particles in the gas is some constant. Okay, so we're assuming the number of gas particles is always n1. Okay, so we're talking here about an ideal gas, right? And we need to write its canonical partition function for an ideal gas. So we know what is the canonical partition function for an ideal gas, right? We know that the canonical partition function for the gas equals to the subsystem partition function for one particle in the gas in the power of the number of particles in the gas, right, divided by L1 factorial because the particles are identical. Great. And we know what this is, a subsystem partition function for one particle, because we just write it on the board, right, in the last question. So we know that this one system subsystem partition function equals to V divided by lambda in the third. Okay, so this is the canonical partition function. So now we move on to section B. Okay, and now we want to write the grand canonical partition function for the NS adsorption sites. Okay, so for the sites, we cannot assume that the number of particles in each site is constant. Okay, we have some constant number of adsorption sites, but in each site we don't have, we cannot assume constant number of particles. Okay, because this is this has a major effect on one adsorption site. Okay, so this is why we're asked to use here the grand canonical partition function, because the number of particles in the site is important. Okay, so we have NS adsorption sites, okay, and each one is like a subsystem, okay, because the adsorption sites don't interact one with each other, right? So we can use here the subsystem partition function for one adsorption site. Okay, so we can write, okay, the total partition function for the total number of adsorption site, this is the grand canonical, equals to the subsystem partition function let's write it as 1, okay, for one adsorption site in the power of the number of adsorption sites we have. Okay, and here we don't need to divide here by NS factorial because the adsorption sites are different one from each other. Okay, they are not identical because they each one sit in different location. Okay, so this is how we can write the total partition function of the system. So now what we need to do is to find the grand canonical partition function for one adsorption site. Okay, so for one adsorption site, first we write the summation. So we need to sum on all possible states on the exponent of minus beta. What we have here, we have the energy of one state minus mu times the number of particles in this state. Okay, what states we have in one adsorption site? So we know that one possible state is when the number of particles in the site is 0. Right? We can have an empty adsorption site. Right? Okay, what is the energy of this state?
0.
Right, so the energy just equals to 0. Okay, the second state is when we have one particle in the adsorption site, and in this case the energy is given to be minus epsilon. And this is the all possible states we have, because the adsorption site can adsorb maximum one particle. So we have only 2 possible states. So we can just do the summation, just write 2 terms, and we don't need to have here some series or something. So this will be equal to, so for the first state, n equals 0 and e equals 0, so just give us exponent in the power of 0. So we have 1. This is for the first state. And for the second state, so e equals to minus epsilon and n equals to 1, so we will have exponent of beta times epsilon plus mu. And this is our partition function for one adsorption site. So the total partition function will be equal to this term. We have the exponent epsilon plus mu, and this will be in the power of the number of the adsorption sites. Okay. So now in the next section we want to find the internal chemical potential of the gas. So now we're talking again about the gas and not on the adsorption sites. And we want to find its chemical potential. Okay, so this is a thermodynamic variable, so we want, so we need first to calculate the free energy of Helmholtz of the gas. Okay, and then we can extract this mu from the energy of the system. So we know mu equals to derivative of n of f relative to n. And we know that f equals to minus kBt ln of the canonical partition function, okay, that we have calculated in the first section. So we can do this algebra and get that this potential, this chemical potential, equals to minus kBt, and what we have here, we have ln of V divided by lambda in the third times n1. Okay, and 1 is the number of particles in the gas.
סליחה.
Okay. So now for the last section, Okay, so now we want to find the average number of particles at a single adsorption site. Average number of particles in a single adsorption site. So we want to find how many particles in average we have in single adsorption site. Okay, so to find this, okay, it's again some thermodynamic size. Okay, we need to find the grand canonical potential, right? But we need to find this potential for a single adsorption site. Okay, so we won't take our total grand canonical partition function because this is for the total number of adsorption sites. We want only for a single one, a single adsorption site. So we will take this subsystem partition function for single adsorption site and calculate the average number of particles relative to this function. Okay, so let's do it like this. So the average number of particles, right, equals to the I forgot the word, the probability. Okay, so this is equals to the probability of the first state times the value of the number of particles in this state, right? Plus the same for the second state, right? So we have for the first state, we have some probability to have 0 particles in the site times the value of 0 particles in the site plus P1 times the value of 1 particle in the site. Okay, we calculate the average because we have only 2 terms. It will be easier to calculate the average like this. So this is times 0, this is cancelled, and our P1 equals to the suitable exponent to the state 1 divided by the whole partition function. Okay, so this is equals to E in the power of beta epsilon plus mu divided by 1 plus E beta plus epsilon mu. Okay, and this is the average number of particles in one adsorption site. Okay, so we have 2 more sections that are less important, so let's just stop here. But what we see is that we can find exactly the same things as we found in the canonical ensemble. Okay, the same method of work, of problem solution. Okay, do you have any questions?
No, this time.
What?
No, this time. Maybe I was thinking of.
Okay.
Okay.
Okay, great.
לא מבינה איך תצליחו לטעות בזה.
כן, זה 7 שנים.
עד שאתה אומר ככה לעשות.
עד
שנתיים.
שמקלינו על זה.
מוריד הכל.
מינוס 4 שנים.
לא, אני אגיד לך את האמת,
בגלל זה אני מתכוונת.
הוא אמר לי כאילו
אבל אולי